You were taught that heat is motion, that when you heat a piece of metal, the atoms inside it start vibrating faster. More energy, more vibration, more movement. And because they're moving more, they need more space. So the metal expands. This explanation is everywhere. It's in textbooks. It's in classrooms. It's probably the first thing that comes to mind when you think about why rails buckle in summer or why bridges have expansion joints, and it sounds perfectly reasonable, except it doesn't actually explain anything. Because here's the problem. If atoms are just vibrating faster, why would that make them take up more room? Imagine a ball on a string. You swing it in a circle. Now you swing it faster. The ball moves quicker, sure, but does the circle get bigger? Not unless something else changes. The radius stays the same. The ball just completes more loops per second. Faster motion doesn't mean more space. It just means faster motion. Now apply that to an atom. It's sitting in its equilibrium position, vibrating back and forth. You add heat. It vibrates faster. Fine. But why does its average position move outward? Why doesn't it just oscillate more rapidly around the exact same spot? If the forces pulling it back toward equilibrium are symmetric, if the restoring force is the same whether the atom moves left or right, in or out, then the average position shouldn't change at all. The atom would just rattle harder in the same location. No expansion, no contraction. Just faster vibration in place. But metals do expand. Glass expands. Almost everything expands when you heat it. So something is missing from the picture. The problem isn't that the explanation is incomplete. The problem is that the explanation is based on a false image. You've been imagining atoms as little spheres bouncing symmetrically in a box, and that image is leading you astray. Feynman understood this. He knew that the vibration itself isn't the cause. Vibration is just the canvas. The cause is what happens during the vibration. It's not about how much the atoms move. It's about where they're allowed to move. And that asymmetry, that bias in the available space, is what changes everything. There's a curve that governs everything about how atoms stick together. It's called the interatomic potential energy curve. And if you've never looked at it closely, you've missed the single most important feature of matter. Here's what it looks like. On the horizontal axis, you have distance, how far apart two atoms are. On the vertical axis, you have potential energy, how much energy is stored in their configuration. At very large distances, the curve is flat. The atoms don't interact. No attraction, no repulsion, just emptiness. As the atoms get closer, the curve dips downward. This is attraction. The atoms want to be near each other. Electrons are shared, or polarized, or doing whatever quantum thing they do. The potential energy drops. This is bonding. At some point, the curve reaches a minimum. This is equilibrium, the natural resting distance between two atoms in a solid. If you leave them alone at the right temperature, this is where they sit. But now here's the critical part. If you try to push the atoms closer together than equilibrium, the curve shoots upward, steeply, violently. The potential energy skyrockets. This is repulsion. Electron clouds start to overlap. Pauli exclusion kicks in. The atoms refuse to occupy the same space. The wall is hard. If you try to pull the atoms farther apart than equilibrium, the curve also rises, but gently, gradually. The attraction weakens as distance increases, but it doesn't fight back with the same ferocity. The bond stretches. Eventually it breaks, but the resistance is softer. This is the asymmetry. The curve is not symmetric around the equilibrium point. It's steep on one side and shallow on the other. Repulsion is a wall, Attraction is a slope. And this asymmetry is not a minor detail. It's not something you can ignore for simplicity's sake. It is the reason thermal expansion exists. Because when an atom vibrates, it doesn't just sit at equilibrium. It oscillates back and forth along this curve. And if the curve were perfectly symmetric, if the steepness were the same on both sides, then the atom would spend equal time on each side, and its average position would remain exactly at equilibrium. But the curve isn't symmetric. So when the atom swings inward towards smaller distances, it hits that steep, repulsive wall. It can't go very far. The energy cost is too high. It bounces back quickly. But when it swings outward toward larger distances, it finds that gentle slope. It can wander farther before the restoring force pulls it back. It spends more time out there. And when you average over many oscillations, the mean position shifts. Not because the atom is vibrating harder, but because the landscape it's vibrating in is tilted. That tilt is why metal expands. Let's be precise about what's happening here. Because this is where intuition completely fails most people. You have an atom, it's vibrating. At any given moment, it's somewhere along that potential energy curve, sometimes closer to its neighbor, sometimes farther away. The vibration is real. The motion is real. But the question is, where is the atom on average? If the potential curve were symmetric, the answer would be simple. The atom would spend equal amounts of time on both sides of equilibrium. Close and far would balance out. The average position would be exactly at the equilibrium distance. Heat the system up, and the atom vibrates more, but the average stays put. That's what your intuition expects. That's the picture in your head. But the curve is not symmetric, and this changes everything about how averages work. When the atom swings inward, it climbs that steep repulsive wall. Potential energy rises fast. Kinetic energy drops fast. The atom slows down as it approaches the wall, then reverses direction before it gets very far. It spends very little time in this region. When the atom swings outward, it climbs that gentle, attractive slope. Potential energy rises slowly. Kinetic energy drops slowly. The atom can drift farther before it has to turn around. It spends more time out here. Now here's the key. The average position is not determined by how far the atom can go in each direction. It's determined by how much time it spends at each distance. And because the atom moves more slowly when it's farther out, because it's climbing a gentler slope, it lingers in that region longer. So even though the atom oscillates back and forth, the time-weighted average position shifts outward. This is Feynman's insight. Thermal expansion is not about atoms needing more space because they're moving faster. It's about atoms spending more time in the regions where the restoring force is weaker. The asymmetry of the potential curve biases the statistical distribution of positions. At low temperatures, the atom barely vibrates. It sits close to the bottom of the potential well. The asymmetry doesn't matter much because the atom never explores the steep or shallow parts of the curve. It just sits near equilibrium. But as you add heat, the atom vibrates more energetically. It explores more of the curve, it climbs higher on both sides, and because one side is steeper than the other, the average position begins to shift. More heat means more exploration. More exploration means more time spent in the asymmetric regions. More asymmetry sampled means more shift in the average. That shift is thermal expansion. It's not that the atoms are pushing each other apart. It's that the statistical center of mass of each atom's oscillation has moved outward, and when you add up billions of atoms, each shifted slightly, the entire lattice stretches. The metal hasn't been inflated. It has been recentered. And the thing that recentered it wasn't the energy. It was the shape of the forces. The energy just gave the atoms enough motion to feel that shape. You heat the metal, and the atoms don't push outward. They drift outward probabilistically because the universe allows them more room on one side than the other. So now the question becomes, why is the potential curve asymmetric in the first place? Why does repulsion rise so steeply when atoms get close, while attraction rises so gently when they're pulled apart? This isn't arbitrary. It's not a coincidence. The asymmetry is built into the quantum mechanical rules that govern how matter behaves, and understanding why reveals something deeper about what matter actually is. Start with repulsion. When two atoms are pushed together, their electron clouds begin to overlap, and electrons obey the Pauli exclusion principle. No two electrons can occupy the same quantum state. So when the clouds overlap, electrons are forced into higher energy states. States they didn't want to be in. States that cost energy. This cost rises extremely fast with decreasing distance. It's not linear. It's not even quadratic. It's exponential or close to it. The closer you push, the more violent the resistance becomes. Electron clouds do not compress gently. They fight back hard. This is why the repulsive side of the curve is so steep. It's quantum mechanics saying no. You cannot put two electrons in the same place. The universe will not allow it, and the energy penalty for trying scales brutally. Now consider attraction. Atoms attract each other because of electromagnetic interactions between nuclei and electrons. These can take different forms: covalent bonds, ionic bonds, metallic bonds, van der Waals forces, but the underlying cause is always electrostatic. Opposite charges attract. Electron density shifts. Energy is lowered when atoms are near each other. But this attraction has a limit. As you pull atoms farther apart, the attraction weakens. In most cases, it falls off with distance. The electromagnetic influence of one atom on another decreases as separation increases. Eventually, if you pull them far enough apart, the bond breaks entirely. The atoms stop interacting. The curve flattens out. This weakening is gradual. There's no hard cutoff, no quantum rule that says beyond this distance, attraction stops immediately. The force just fades. The slope of the potential curve becomes gentler as you move to larger distances. So you have two fundamentally different behaviors. Repulsion is a quantum wall enforced by exclusion. Attraction is an electromagnetic gradient that softens with distance. One is abrupt, one is gradual, one is steep, one is shallow. The asymmetry isn't a design choice. It's a consequence of the fact that exclusion and attraction have different mathematical forms. Exclusion is a hard quantum constraint. Attraction is a fading electromagnetic influence, and because of this, the forces holding matter together are not symmetric springs. They're anharmonic. They're biased. They have shape. If the universe worked differently, if exclusion were softer, or attraction were steeper, then the curve might be more symmetric. But the universe doesn't work differently. This is how quantum mechanics and electromagnetism combine. This is the only way matter can exist. And because the curve has this shape, thermal expansion is inevitable. You can't have matter without asymmetry. And you can't have asymmetry without expansion when energy is added. The fact that metal expands when you heat it is not a property of metal. It's a property of the rules that make matter possible. There's a model you were probably taught, maybe in high school, maybe in an introductory physics course. It's called the harmonic oscillator. You imagine atoms connected by springs, perfect, ideal springs. You pull on one, and the restoring force is proportional to the displacement. Pull twice as far, get twice the force. Push instead of pull, same thing. The spring doesn't care which direction you go. It just pulls back with a force that depends linearly on how far you've moved from equilibrium. This is Hooke's law. And it's elegant. It's mathematically simple. It makes the math of vibrations tractable. You can solve it exactly. You can predict frequencies, modes, energy levels. It's the foundation of how we teach oscillations. And it's a lie, not a useful approximation, not a simplification that works well enough. A lie. Because a harmonic oscillator, a perfect spring, is symmetric. If you plot its potential energy, you get a parabola. Smooth. Symmetric. The same curvature on both sides of equilibrium. And if atoms really behaved like this, there would be no thermal expansion. None. You could heat a harmonic solid to any temperature you wanted, and it would not expand. The atoms would vibrate more energetically, sure. They'd explore larger displacements, but the average position would remain exactly at equilibrium because the potential is symmetric. The harmonic oscillator model predicts zero thermal expansion. And yet we teach it anyway. We teach it because it's simple, because it's solvable, because for small vibrations, it's close enough to reality that you can pretend it's true. But the moment you ask why materials expand, the harmonic model becomes useless, worse than useless, actively misleading, because real interatomic potentials are not parabolas. They're anharmonic. The curvature changes depending on which side of equilibrium you're on. The restoring force is not proportional to displacement. It's stronger when you compress, weaker when you stretch. This anharmonicity is not a small correction. It's not something you add later to make the model slightly more accurate. It's the entire reason expansion exists. If you treat atoms as harmonic oscillators, you are using a model that is incapable of explaining the phenomenon you're trying to understand. You might as well use a model that assumes atoms don't move at all. And yet the harmonic model persists because it's convenient, because it gives students something to calculate, because admitting that the real world is anharmonic makes everything harder. But harder doesn't mean optional. The universe is not a collection of springs. Atoms do not oscillate symmetrically. The forces are shaped by quantum mechanics and electromagnetism, and those forces have structure. They have steep sides and shallow sides. They have walls and slopes. And once you accept that, once you let go of the spring analogy, the mystery of thermal expansion dissolves. It's not that heating adds more vibration. It's that heating lets atoms sample the anharmonic regions of the potential, and those regions are biased. The spring model is seductive because it's simple. But simplicity is not the same as truth. And the truth is this: if atoms were springs, nothing would expand. The fact that everything does expand is proof that they're not. Imagine a universe where the interatomic potential curve is perfectly symmetric. Repulsion and attraction have the same shape, the same steepness, the same curvature on both sides of equilibrium. You push atoms together, and the energy rises at a certain rate. You pull them apart, and the energy rises at the exact same rate. A perfect parabola, a perfect spring. This universe obeys all the same laws of thermodynamics. Energy is conserved. Entropy increases. Heat flows from hot to cold. Atoms still vibrate. Temperature still exists. But nothing expands. You take a metal rod in this universe and heat it. The atoms absorb energy. They begin to oscillate more vigorously. The amplitude of vibration increases. The kinetic energy increases. Everything you associate with heating happens, except the rod stays exactly the same length. Because the average position of each atom doesn't shift. The atom spends just as much time closer to its neighbor as it does farther away. The statistical center of the oscillation remains locked at equilibrium, no matter how hot the material gets. There are no expansion joints on bridges in this universe, no gaps in railroad tracks, no thermometers because liquid columns don't rise with temperature, no bimetallic strips bending to open or close circuits. The entire technology of thermal expansion, everything that relies on materials changing size with temperature, simply does not exist, and it's not just technology. The physics is different too. Pressure would behave strangely. Normally, when you heat a gas at constant volume, the pressure increases partly because the molecules are moving faster, but also because they're effectively taking up more space due to anharmonic interactions. In a symmetric universe, that second effect disappears. The equation of state changes. Phase transitions would be different. The way solids melt, the way liquids boil, these depend on how atomic spacing changes with temperature. In a symmetric universe, spacing doesn't change. The structure of matter near phase boundaries would be unrecognizable. Even the Earth would be different. Geothermal gradients drive convection in the mantle, partly because hot rock is less dense than cold rock. But if rock didn't expand when heated, there would be no density difference, no convection, no plate tectonics. The entire geological history of the planet would be altered. You start to realize that thermal expansion isn't some minor side effect. It's woven into the structure of physical reality. It's a consequence of the fact that forces are not symmetric, and that asymmetry shapes everything. And here's the strangest part. This symmetric universe isn't impossible. It doesn't violate any fundamental conservation laws. You could write down the equations. You could simulate it. Mathematically, it's perfectly consistent. It just isn't the universe we live in. The asymmetry is not required by logic. It's required by the specific forms of quantum mechanics and electromagnetism that happen to govern our reality. The Pauli exclusion principle could have been different. Electromagnetic interactions could have scaled differently with distance. The rules could have been otherwise, but they're not. And because they're not, atoms can't oscillate symmetrically. And because atoms can't oscillate symmetrically, the average position shifts with temperature. And because the average position shifts, matter expands. Remove the asymmetry, and you remove thermal expansion. Keep the asymmetry, and expansion is inevitable. We live in the universe with the asymmetry. And that one fact, one shape of one curve, determines whether a metal rod gets longer when you heat it. There's one more place to look. One more extreme to test the idea. Not absolute zero. The coldest possible temperature. The point where, classically, all motion should stop. No vibration, no kinetic energy. Just atoms sitting perfectly still at their equilibrium positions. If thermal expansion's caused by atoms exploring the asymmetric regions of the potential curve, then at absolute zero there should be no expansion at all. The atoms aren't moving. They aren't sampling anything. They're frozen. Except they're not. Even at absolute zero, atoms still move. Quantum mechanics doesn't allow them to stop completely. There's something called zero-point energy, a minimum amount of motion that persists even when you've removed every bit of thermal energy you possibly can. This isn't thermal motion. It's quantum motion. It exists because of the Heisenberg uncertainty principle. If an atom were perfectly still, you'd know both its position and its momentum exactly, and that's not allowed. So even at the absolute bottom of the temperature scale, atoms oscillate. Just a little. Just enough to satisfy uncertainty. And here's the critical question. Does this zero-point motion cause expansion? No, because zero-point motion isn't statistical. It's not a matter of the atom sometimes being here and sometimes being there, with more time spent on one side. At absolute zero, the atom is in its quantum ground state. It's in the lowest possible energy level. And in that state, the probability distribution is centered exactly at the minimum of the potential well. There's no thermal averaging over asymmetric regions. There's no drift. The atom occupies a quantum state, and that state has a most probable position, and that position is at equilibrium. Zero-point motion gives the atom a spread, a quantum fuzziness, but that spread is symmetric. The atom is equally likely to be found slightly closer or slightly farther from its neighbor. The average is still equilibrium. So even though the atom is moving, even though it has energy, there's no expansion. Expansion requires heat, not motion. Heat. Because heat is what drives the atom up the sides of the potential curve into the regions where asymmetry dominates. Heat is what populates higher energy states, where the atom spends time exploring the steep repulsive wall and the shallow attractive slope. Heat is what breaks the symmetry of the ground state probability distribution. At absolute zero, the atom is moving, but it's trapped in the lowest energy state. It can't explore. It can't wander. It sits at the bottom of the well, vibrating in place with the minimum quantum jitter required by the universe, and nothing more. Thermal expansion is not about motion. It's about statistical wandering in a tilted landscape, and wandering requires energy to lift the atom out of the ground state. It requires temperature. Remove the temperature, and the wandering stops. The atom still moves, but it no longer drifts. The average locks in place. This is the silence of equilibrium. At absolute zero, the asymmetry is still there. The potential curve is still tilted. The repulsive wall is still steep, and the attractive slope is still shallow. Nothing about the forces has changed. But without heat, the asymmetry has nothing to act on. The atom never climbs high enough to feel the difference. It never samples the regions where the bias would matter. And so it sits, motionless in a quantum sense, moving but not expanding. The metal is as small as it will ever be, and the only reason it expands at any other temperature is because the universe built an asymmetry into the forces and then gave atoms the energy to feel it. Expansion is not a property of heat. It's a property of exploring an asymmetric world with thermal energy. And once you see that, once you understand that the shape of the curve is the cause and temperature is just the means of exploration, you realize that everything you thought you understood about why things get bigger when they get hotter was backward. The atoms aren't pushing, they're wandering, and the universe is tilted.